Recording in progress.
All right. So we'll continue from where we left off. I'm going to be showing you a lot of different things in the microwave office software. So just try to make a note of these things and do try them when you go back so that you get used to these things. I'll be giving you the first assignment either this weekend or early next week. And some of those problems will require you to use microwave office. So it's a good time to start getting familiar with it if you have not already done so far. Okay, so last time we were discussing the different types of transmission lines, and we looked at the coaxial transmission line in some detail. And we were looking at this tool, which you can access from inside microwave office in this tools menu called TX line. It's actually a separate program, and you can find it somewhere in the installation files, and you can run it separately, independent of microwave office as well. Yeah. This one there. Yeah, so we use the round coaxial tool, and we saw some reason it's not updating. Right. And we looked at how the characteristic impedance changes with the inner and outer diameter. Earlier, we had seen the mathematical form, which is like log B over A. And using this tool, we saw how the different parameters affect which quantities. And we focused on two things. The characteristic impedance, of course, is the main thing we are mostly interested in. But the other thing is the electrical length, and especially the connection between the physical length and the electrical length. Because as we have seen, lambda by 4, lambda by 2 have special properties, and we're going to be using those sections later on to build different kinds of circuits. So it's important to know when you're actually making these devices, what is the actual length you need. And this kind of tool helps you to get started. As I also mentioned that they are not 100% accurate, you might not get things working at the percent level, but definitely at the 5 to 10% level, matching will definitely be there. For more accurate estimates, you can use finite element simulations as well, which I will introduce today on how to use it in microwave office. Okay. So we then very quickly looked at the strip line, the micro strip line, and also the CPW. So we'll spend a little bit more time looking at those things again. So strip line here is basically a center conductor which is buried inside a dielectric, and there are two ground planes on either side. So I also mentioned that you can sort of think of this as a coaxial thing which is sort of been cut open from both sides and stretched out. and turned into something like this, and then you turn this also into a rectangular piece. So it's sort of like a coaxial thing. And one of the important aspects I had mentioned is that, again, the field lines exist entirely inside the dielectric medium between the metallic plates, the two top bottom and the top ground planes and the center one. And because of that, in this tool, the effective dielectric constant comes out to be the same as what you have mentioned here. Just to remind you of that, you see this dielectric constant 3 and the effective dielectric constant comes out to be the same. So this is just some internal calculation number which is used to compute this. But so just so that you're not confused by what's going on with this number, we also saw what happens when you have field lines in both air and dielectric. Then you get some effective number here, which is smaller than the true dielectric constant of the main dielectric in the system. But obviously, there's nothing called main dielectric. There is a substrate on which you have to design these things. And if the structure of the transmission line is such that the field lines have to exist in air, then you have to take that into account. Okay. But this is of no, there's no significance to worry about that number when you're actually using this as a tool. It's just present there. I will show you in some other context why this number sometimes becomes important, just to see that it's different in two different cases. And mostly it tells you about the participation of the dielectric and the air in different proportions, and that can have a significance on certain properties. Okay, so just like the coaxial, you had basically the inner diameter and the outside diameter, which basically allowed you to parameterize this gap region between the two conductors. For the case of the strip line, you have the total gap between the two, or you can equivalently just say that it's the gap between the center conductor and the ground plane times 2. So B can always define it as B by 2 and B by 2. And then you have the width of the center conductor. That sort of plays the role of the diameter of the center conductor for the coaxial line. Okay, it's not exactly the same. But again, just from the intuition we have been developing, you can realize that there are only two main dimensions here, the total gap and the width. So if the width becomes larger, the capacitance is going to increase, the inductance is going to decrease, and then vice versa. And if your gap becomes larger, the capacitance is going to decrease, and the inductance is going to increase because of the shielding effect going away as the ground planes go further apart from each other. Okay. So that allows you to basically figure out that if you are trying to make a 50 ohm strip line, transmission line, or some other impedance, how to choose the numbers and get to 50 ohms. So for example, whatever numbers were here, it's giving me an impedance of 70 ohms at a frequency of 10 gigahertz. So if I want to bring it closer to 50 ohms, I can increase the thickness a little bit, and that will bring it down. You can go. So almost need something like 0.55 millimeters for a total height of about 1 millimeter. So you can see the aspect ratio is actually quite in this. It's sort of the plates are quite close to each other in order to get 50 ohms. Part of this is of course related to the relatively low dielectric constant we have used here of 3. If this was higher, then automatically the widths will become less. So let's try for 6. Now this impedance is going to be much smaller. So you need to reduce the to get to about 50 ohms. Right? So, okay. And the electrical length here basically is connected to the physical length you have specified here. And as I told you, you can also calculate in both directions. You can specify what you need, and then it will give you the dimensions. Obviously, it doesn't change all of them. For strip line, it'll mostly just change the width and not the height, because it's assumed that the height is going to be set by whatever material you have chosen to make this strip line. So as a designer of a microwave transmission line, you have some constraints, that you have some material to choose from, and then the only design parameter you need is the width of the center line. So that's why if I put this to 50 ohms and do the calculation in reverse, it's not going to touch the height or the thickness of the center film, because that is again decided by the choice of the board. So last time I had circulated those boards, so they are from a specific company. This is a specific model, has a specific dielectric constant, thickness of the coating of the copper on it. And these are things you specify when you buy this circuit board from the company. So that's why the calculation only messes around with the width, because that's really the only design parameter you have in your control. Okay, so the strip line, as I was mentioning, is not a very convenient transmission line to use, because if you imagine what you're going to see from the outside is just two ground planes, right? The center conductor is not going to be visible because it's buried underneath. It's only going to be visible at the edges. So if you have the end of the transmission line, so these kind of transmission lines are useful in scenarios where you're only connecting to them at the edges, okay, which could be perfectly fine. For example, if you're making some kind of a transformer, say a λ/4 transformer, and that only has connections at the two ends, there's nothing happening in between. But if you're designing some high frequency circuit where you have some components, maybe you have a transistor, you're making an amplifier and it has to be connected, then the strip line becomes inconvenient because there's no simple way to access the center conductor. And that's where the microstrip line, which I had introduced last time, and we'll look at it a little bit later today also, is convenient because you remove the top ground plane and the top dielectric, and then you have the center conductor exposed. So then it becomes easier to connect, even though not as easy as a third type of transmission line, which is the CPW transmission line, where both the ground plane and the center conductor are on the same surface. So then it's very easy to connect components across it. And it's actually quite a popular choice of transmission line because of that as well. Okay. But between microstrip and strip line, this difference that the field lines are entirely inside the dielectric and only one type of dielectric for the strip line, versus the fact that the microstrip line has field lines in air, actually changes the nature of the transmission line itself, in the sense that the modes which are propagating on microstrip are called quasi-TEM. They are not exactly TEM. So there is some extra aspects to the way the field lines are, and that has an effect on how the waves propagate. So the dispersion is not completely absent, but it's low enough that at the kind of frequencies one is working at, typically it's not a huge bother. It doesn't make such a big difference. But there are some specific types of microwave devices where this difference can actually make the microstrip basically not usable. Okay. And this is a device which is called a directional coupler, and that uses two transmission lines coupled to each other in order to perform the necessary action. And this is one of the devices we'll be studying in detail later on, but it's a 4-port device. So it's basically just two transmission lines close to each other. So, and each transmission line has 2 ports, and you are able to achieve a certain kind of property which you want from that particular device. Okay, so that's the strip line. And so let's move on to the microstrip very quickly, just to remind you of the structure. So no top ground plane. And the main difference is that if I now look at this effective dielectric constant, it's 4.45 for something which is specified to be 6. Right? It's lower because now part of the field line is in the in air as well. Okay, and then finally we looked at CPW and CPW ground. The only difference is that in CPW ground, there is ground plane underneath. So it's sort of like a microstrip, but with two additional ground planes on the side, like these two. So if you ignore these two guys on the side, then this just looks like a microstrip. Okay. But if you include them, what it means is that there is now more field lines. So there's field lines going this way, but there's now field lines going like this also to the side ground plane. So this one is now sort of like a, if you again start with the coax, this one is like a half coax, right? You can imagine this to be like this. Especially if one includes a certain feature, which I forget if I mentioned the idea of vias, that in a CPW, the two ground planes on either side have to be at the same potential. So, and this is not something that's going to happen automatically. So remember again, the thing I've been going on and on about, if I give a potential to a section of metal at one point, it doesn't mean that even if it's a perfect conductor at RF frequencies, the potential can change along with, as if your distances are comparable to the wavelength. So in order to keep the two the two ground planes on either side at the same potential, what one actually does, let me actually draw this here in a bigger size. So that's the bottom ground plane. That's your center conductor, and this is your side ground plane. So in order for these two to be at the same potentials, one either uses air bridges, which are actually wires which go from the top like this, and you can connect them at periodic intervals along the length of the transmission line. So here into and out of the board, or you can make connections through the dielectric, a metallic connection like this. These are called vias. This is an air bridge. And then this here is called a via. It connects electrically the top ground planes to the bottom ground plane. And because the bottom ground plane is continuous, effectively it creates a connection between this side and this side. So that's why I said that this sort of looks like a half coax, where the ground plane is there. So this means that the effective capacitance is going to be related to both this height, capacitance per unit length, and also this gap. Which, if the dielectric constant of the bottom material was, let's say, a high value like 10, let's say the relative permittivity was 10, which dimension, the height or the gap between the electrodes will, like changing which one of them will change the capacitance faster? Yeah, again. It's not a complicated question. Go ahead. It's, if you say something wrong, it's okay. You can say it. Huh? Maybe. Why height? You obviously, the answer is right, but you must have thought of a reason. Sort of. So because the dielectric constant is high there, that part of the structure is going to contribute to the capacitance more, because it's going to be 10 times higher than the capacitance through free space for the similar dimensions, right? So changing the height will affect the capacitance per unit length a lot more than changing the width. It's not as simple as that, because the width part of the transmission line, if this ground plane was not there, the bottom ground plane, there are field lines going both above and below, right? And in fact, the field lines will predominantly go below the dielectric, because that's where the field lines can penetrate a lot easier. But it will still, it's not like a parallel, simple parallel plate capacitor, and the air also plays a role. So obviously this dimension will have some a dominant effect. Okay. So, but you can also have the version where, you know, you cannot get rid of the dielectric, but you have basically a finite dielectric thickness and no ground plane underneath this. So this is slightly an artificial, maybe let me see how to say this. So right now, this substrate just looks like a slab of dielectric with some metal patterns on the top, right? One can make this, but usually these kind of structures sit on some other box, which is usually metallic. So not having a coating of a metal underneath the chip is of no consequence if that chip is actually sitting on a metallic piece, because then that gives you the ground plane. So one has to be careful about these kind of aspects when one is designing, because if it's sitting on a metal, it's actually the same as a CPW G system. Now there are some scenarios where even if a ground plane is present at the bottom, it will not play a dominant role, and it will actually look more like a CPW as opposed to a CPWG. What kind of a situation would give rise to such an effect? Let me elaborate a little bit. So let's see what are the dimensions here. Okay, 50, 50. So this is CPW, and it's giving me a 50 ohm transmission line for these parameters. If I go to CPWG, and you see that for the same dimension, the characteristic impedance is 48 ohms. Now, does that make sense? That for CPW, everything is the same, right? The only difference is in CPW, there's no ground plane at the bottom, and it's giving me 50 ohms, and CPWG is giving me 48 ohms. Does that make sense? Why is that? Higher capacitance, because now you have an additional mechanism for getting capacitance to ground. Okay, it's not a very big difference, but it is still there. So what I'm asking is, under what condition these two will give you the same number, or like a very, very small, insignificant difference, even smaller than what you're seeing right now? Yes, and that would happen when? Yeah. So either the dielectric is very thick, which means that the field lines don't really get to see the ground plane, or the gap is very, very small, because then the dominant field lines, this takes over, and then there is no need for the field lines to sort of see the presence of the other ground plane. And that's sort of the more realistic scenario where the this CPW without the ground plane comes in. But you can use either of those tools and you'll get the same answer. Okay. So these relative dimensions play a role. And in the context of CPW, I had also mentioned that one very nice thing about CPW is that you can get 50 ohms for very different combinations of the gap and the width, right? Because both you can change, and both of them are, on the surface. So what I mean is that you could start with something which looks like this, and then you can narrow this to something very small. And in order to maintain 50 ohms, you reduce the gap between the two as well, and you bring it something close. I mean, this is a horrible drawing, but you know what I mean. You saw these things I had shown you last time. So you can do a taper. And this dimension difference can be like 2 orders of magnitude. And it still works really, really well. So these are very useful where you have microscopic devices you're trying to study, or like some very small surface mount components which you want to do. But usually even any component you're going to work with has to be handleable by hand or some small instrument. So usually this happens in more special research kind of devices, where the actual device size is very small. Maybe it's only like a few microns, a few tens of microns long. Whereas the other end, so that device will go here somewhere, device end. But here you want to connect it to some connector where you can bring your signal in. So it has to be much bigger. And this transition has to be smooth. 50 ohms have to be maintained. So CPW allows you to do that. Now, even microstrip allows you to do that, because there you only have to, actually, no, microstrip doesn't allow you to do that, because if you reduce the center width, there's no way to change the height, because that's the only other dimension you have. So that's why you need this other control, which the CPW allows you to do. So I'll show you later on some images of such devices where you start from a very large CPW and then go down to a very narrow CPW. These kind of devices are used in our lab quite routinely. Okay. So right, yeah. So this was CPW and CPW ground. So the rest, all these things are the same. Again, for both CPW and CPW ground, the effective dielectric constant is different than the true dielectric constant. That's just because now you have field lines present in the air, right? There is another kind of transmission line which is not used that much, but it's useful to know. And this is what is called a slot line transmission line. Okay, so if you see the picture here, let me draw it again. So it's just basically a very large metal plane on either side with just a gap in the middle. Okay, so this is, in some sense, I guess the closest is to think of just 2 wires next to each other, but it's a little bit different than that, because the ground planes here are considered to be, at least in the idealized model, to be infinite in dimension. So it's very big and the slot is very small. And then the field lines are basically inside this kind of a medium. This has an indirect consequence on understanding of the CPW mode. So that's why I'm discussing this here. And again, the only relevant dimension here is basically the gap between the metal and the height from of this substrate, right? This particular height here. Why does that matter? It's basically, again, the same idea that how much are the field lines going to penetrate. If that dielectric is very thin and there's something else, then it will start feeling that, which could just be the absence of a dielectric, which means like there is air here on this side, or if you have a metal plane. So obviously in the ideal slot line, there is no metal in that model, but you could have a metal there, but then it's no longer a simple slot line. And I'll show you an example which will explain this in just a little bit. Okay. So you can then just look at this, and so it gives some warnings here saying that G over lambda naught must be greater than something. That means the gap should not be too large, I guess, not too small. H, sorry. Doesn't like all the overall dimensions to be too small. 200 microns gap and a height of 1 millimeter. It's giving me 87 ohms. I need, if I want to go to 50 ohms. It'll be very hard to get 50 ohms in this. maybe it is difficult to get 50 ohms in this kind of a geometry. Could do this by increasing the, yeah, but then it complains about. So this is actually now giving you some kind of a constraint that for this geometry, it's harder to reach 50 ohms because of other considerations which are related to the wavelength and the dimension of the. I actually don't remember, because I haven't looked at the slot line in a very long time, why that warning is there. So it's basically saying that the gap has to be greater than, the gap divided by the wavelength has to be greater than some number, because I think the otherwise the mode which you are propagating is probably no longer simply valid. But the reason I wanted to introduce you to this mode, we rarely is used, is actually to consider what happens in a CPW. Okay, let me draw the CPW thing again over here. And let me draw the slot line at the top. The point I made about the vias and the air bridges, that the two sides of the ground plane for a CPW have to be at the same potential, is precisely to prevent the propagation of signals via the slot line mode. If you sort of ignore the center conductor of the CPW, then if these two conductors are allowed to develop a potential difference, then that's exactly what the slot line mode is, right? Because here, in order for the wave to propagate, there has to be some potential difference across these two conductors, right? Obviously, it'll happen at the edge, and then you won't have much penetration inside. So you can have the same thing happen over here. If you develop a delta V on this, that's actually another propagation mode. It's not exactly the same slot line because there is a metal in between, but this is something you don't want at all. For the CPW, what you would like is that the two potential on either side, so this has to be like minus and minus, and then this has to be plus relative to each other, right? So these two at the same minus, and then the center one just has a voltage difference with respect to the same potential on either of the ground plane. But if you have a slot line mode, then that means that this minus and this minus are no longer the same. In the ideal case, this is some plus and this is minus, or vice versa. So in order to prevent this slot line mode, and what basically it means is that you might excite with a certain frequency, and if at that frequency the slot line mode is allowed, then this transmission line is no longer a simple one type of transmission line. It's both a CPW and a slot line. And that means that the characteristic impedance of the net propagation will change, and your field lines will go all over the place, and then you will not get the system you want. You typically end up getting some kind of a resonance when you don't do this. So that's the reason why you have to connect those air bridges or do the vias, which I mentioned earlier. So that ensures that the two metals on the either side of the ground of the center conductor are always at the same potential, and hence the slot line mode is suppressed. Okay, so this is very crucial for any CPW transmission line if it is long enough. So long enough means that anything with some reasonable fraction like lambda by 10 or lambda by 4, it's already too long, right? So if it's a very short section of transmission line, you can get away with it because there's not enough distance for the potential to change significantly. But any reasonable length, you have to make sure that these vias or air bridges are there, otherwise it just wouldn't work properly. So there is one other aspect of the slot line mode, which is that it's a differential mode because it's like plus minus, there is no ground. So for two terminal devices, sometimes it's useful to have these kind of modes. And I actually, back in my grad school days, did use a circuit which had a slot line coming from a CPW, actually a transition from a CPW to a slot line mode, because I wanted only two conductors to be present. And the CPW ideally has three. because there's two ground planes and one. So there are basically you do something like, so you start with the CPW, and then you take this one and you sort of take it away, and then you bring this one to this side, and then you sort of do something like this. And again, all of these have to be done very smoothly over a sufficiently long distance that this ground plane now sort of falls out of action, and then you only are left with the original center conductor of the. So it was something like, plus minus minus in the beginning, and now this becomes some plus, maybe plus prime and minus prime. And then you can put your device across here. So this is something one can use if you need to excite a differential. But there are actually other simpler ways of doing that, which I'm not sure why we didn't do it at that time. One simple way with a CPW is to just do something like this. So you bring the ground plane and you close it up like that. And then you can put your device here. Okay. That's exactly what you want between the center conductor and the ground. And the grounds are anyway, as I said, these are stitched together. And then at the end, you actually make the top conductor itself come around it. So this is all ground plane. So this is another way of doing this. Okay, I think I will not discuss this. Maybe I'll just mention this. There are two other things which are shown here. One is called a coupled microstrip line and a coupled strip line. So it's self-explanatory what the difference between the two is. It's basically, this one has a top ground plane and the full dielectric, and this one doesn't have. But these is now two transmission lines, as I was mentioning. There is one transmission line here and another transmission line here, but they are very close to each other, which means that the field lines are going to talk to each other. So they are not really independent systems. And this kind of a structure has typically two different modes of propagation. That's why if you see here, there is this radio button to select which mode you're interested in, which is the even mode or the odd mode. And it's very simple to understand. What it means is that let's start first with just a single microstrip. There is only one mode which has some plus here and some minus here. Or if you want to think that this is ground, so this is 0, and then this is plus, right? So you have some potential difference developed across these two terminals and changing along the length. Now, if you introduce a second one, now you have to sort of think of this as some kind of a normal mode decomposition. So what's going to happen is that you can have a situation where you have plus 0 and plus 0, where these two have the same potential and they're both going up and down with respect to the ground plane. That's what's called the even mode, where they both go together. But you can also have a situation where this is plus and this one is minus. So the ground plane is at some potential. These two in the even mode go up and down like this. Now they go like this. So if this goes up, that goes down. And the most general propagation will be some combination of these two things. And that's basically, you can convince yourself that if this one had a potential V1 and this one had a potential V2, you can always rewrite this in terms of V1 plus V2 and V1 minus V2. They're two different variables. They give you the same thing. And that's what is called the even and the odd mode. And one can create a situation where only that particular mode is excited. Like if you create the excitation at the edges when you're launching the wave, if you launch it in such a way that the two potentials on both the conductors is the same, then that will only propagate the even mode. If you do it in such a way that the two potentials are exactly equal and opposite, then it will only launch the odd mode. and these two propagate independent of each other. What that means is that if I send in an even mode excitation, it will remain an even mode excitation, and the same for an odd mode excitation. I mean, this might seem like an odd thing to say, but remember the two things are interacting with each other, right? So there is no reason why they would do that. So in general, if you have a arbitrary excitation, then you have both even and odd modes, and they will stay how they are. But for example, if you only excited one of the signals and not the other, then after some distance, the second conductor will also develop a potential difference. Yeah.
How exactly do I imagine this even which is because the voltages are same,
yeah,
or different, they say even and odd?
Yes. So if I now sort of draw a cross-sectional, I mean, a sort of a side view, what that means is that if you think of these two as independent transmission lines, which means that you have to write V of X or V of Z along the line. For the even mode, they will always be the same on both the transmission lines. For the odd mode, they will be equal and opposite. Okay. But because of this difference, the effective field lines participation in the dielectric actually changes for a microstrip line. And that means that the even and the odd mode in a microstrip line for the coupled microstrip line, the velocities, the phase velocities are different. This was the point I had mentioned earlier, whereas for the strip line, it will not be the case. So we can actually look at this here using the tool. So if you look at this phase constant here, it's giving some, 30. Give it some better. Like 780 degrees per inch. If I now go to the odd mode, it is 708 degrees per inch. Just because the velocities are, phase velocities are different. So what that means is that the same physical length corresponds to different electrical lengths for the even and the odd mode, because the speed is different. And this creates a problem. And this is basically because the microstrip is not a true PEM mode, and there is this participation of air and dielectric in different combination. This does not happen, however, in the strip line version of the coupled system. So when I look at the even mode, it's 915 phase constant. Look at the odd mode, it's also 915 phase constant. So this particular device I mentioned, the directional coupler, actually utilizes some interference between the even and the odd mode, and that doesn't work very well in microstrip because at the same wavelength, the lengths, electrical lengths are different. So they don't, the condition is not matched simultaneously for both the even and the odd mode. So we will see that later on in much more detail. Okay. So I just wanted to mention the concept of the even and the odd mode here. And we will now spend the rest of the time looking at how to make these structures in microwave office and simulate them. I will send the video recording link for this lecture to you so that you can revise the details on how to actually run this on microwave office, because there will be many things we'll be doing. So I'll show you two sets of levels of simulations. The first is still a circuit schematic simulation, but this uses a physical model as opposed to the electrical model we have been using so far. So by electrical model, I mean the ones we were using from this element and then only specifying the frequency and the electrical length in order to get the transmission line. So this one. Right, so this is what we're using. There's no physical length here. Now, let me show you So you have to now choose. So these are over here. So you can see coplanar over there and microstrip over here and strip line over here. Okay, so let's start with microstrip. Easy. And it now gives you several kinds of components you can build with this. These are all now physical models of different types of structure. Right now, we're only interested in lines because we're just looking at the strain simple transmission line. Here again, there's like a huge number of varieties of things you can use. There's no way, even I don't even know most of these things. We use the simplest ones, which is this one here, microstrip. So essentially, you can, you can read the help inside of these different materials if you are interested, but it allows you different levels of approximations in the physical model, like what all details you want to specify. And the other ones here are related to different kinds of structures. Like, so this one is a junction. It's a T junction. So it's modeling how a microstrip line will come in and split into two. So it gives a physical model for that. Then there are couple lines, which is exactly what we're looking at. So two lines next to each other. But right now we just, the way one uses them is exactly the same as what I'm going to show you right now. Okay. So I went to the lines and I used this MLin microstrip closed line form. So you see here, it gives me two numbers to specify: the width, okay, that's the width of the microstrip line, and the length of the microstrip line. There's something missing here, which is what? Priyanka, is this enough to specify my microstrip line? So remember this, the simpler model has the one where you specify the impedance and the frequency and the electrical length. Now we have a physical model, which means we are defining the geometry of the system, right? So what all numbers define the geometry of a microstrip transmission line? Like what's missing here? The height is missing, and no, so here the impedance will come once we specify the dimensions, right? So we're going to choose the dimensions to get the impedance we want, which is what we did with this TX line too, right? So height is missing, but the dielectric constant is also missing. So essentially what's missing is the substrate information. Okay, so you have to specify that separately, and it's a sort of an odd way of doing this. Let me get rid of this. Let's see if I remember where to find it. Yeah. So right here, there is substrates. And you have to choose the right type of substrate. And that one can usually find by going to the help here. And it will tell you the type of substrate definition it needs. It can actually be several types. But it will say substrate definition M sub. Okay, and N sub is what is here in this substrate list. So you just drag that also here, and this just needs to be in the same schematic. That's all, and it'll automatically link. So now you see this has many more properties. The reason they have done it like this is because usually the substrate is a separate thing you buy, and then you design your microstrip on top of that. So this right side is the design part, the length and the width, and the substrate is the material we are buying. So you have the dielectric constant, you have the height, you have the thickness of the metal, which is on it, you have the resistivity of that metal. So it tells you the conductivity, like what conductor losses you have. You have tan delta of the dielectric. So this is the losses associated with the dielectric. And this ER nominal is, I think, some internal number. I don't know why they have used this. Actually, let's quickly check what it says in the help. Okay, so here they have given you the diagram of what those numbers means. Height is explanatory. Rho tells you the conductivity of both the ground plane and the top metal, and the dielectric constant and tan delta of the thing. Yeah, so I don't know what nominal relative dielectric constant means. Maybe it's some default value or something, but that's a number which you don't have to change. So let's go back to the TX line, which has disappeared now. Or what? Yeah.
What if you have multiple exceedingly different periods? How would you know that this one corresponds to, how would you tell it?
So that is going to be tricky to make in one schematic, but you can actually make two different schematics and then connect them together. There's a way to do that in microwave office, but that's usually going to be very rare situation, because if you're making any circuit, the substrate is going to be the same. You're not going to make a thick substrate and the thin substrate of different materials and then stick them together. It's very rare. There is one very practical things, for example, the examples I showed you last time. The circuit board takes the coaxial signals onto a planar geometry. Okay, but that's still the circuit board. In our lab, the devices are made on a different substrate, usually silicon or sapphire. Now that will also have its own microstrip or CPW structures, and then the two have to be connected to each other. So that's a perfectly valid example of the situation you're talking about, where you have going from one substrate to another substrate. Now that cannot be directly modeled inside a single thing here. It might be possible to do it with one of the more other options here, because there is a name associated with the substrate called sub1. So it should be possible to specify that in this thing that this should use sub1, but I think it's not allowed in the simplest model here, because it uses this M sub as the default thing. But those kind of simulations in this physical model where you have different substrate might have other complications, because it's not just about the signals from the center conductor, but how the grounds are interfacing. That could be complicated. So it's best that you do a full EM structure simulation where the whole thing is completely defined. Okay. So let's look at that. I'm going back to the TX line to basically get a reference for a model. I'm going to use a dielectric constant of 6. What's going on with this thing? The arrows are not showing up. What's going on? I lost connection. It's become really slow. Yeah. bizarre. All right, anyway, we'll guess some numbers and see what we get. So let's do 606, that the constant of 6. Okay, I can use the numbers I remember from my lab. Height is 762. Thickness is 35 microns. I'm going to put the resistive to be 0. I don't care about the loss. Tan dot is 0. And the set is also the 6. And if I remember correctly, you need something quite wide to get lithiums. Let's make the length 10,000. All right, so define the substrate. We have to define the dimensions. Now the question is, how does one now see whether this is 50 ohm transmission line or not? Any ideas? Sorry? Yeah, but what should I measure? So there are a couple of possibilities. I could do a 2-port simulation, or I could do a 1-port. So if I put 1 port here and I put a 50 ohm on the other end, then if this was a 50 ohm transmission line, then you should get no reflection, right? If it is not a 50 ohm transmission line, then you will get reflection. So we can then adjust the parameters till we get no reflection or very small reflection. So we'll go to lump element, take a load. Okay. Define the frequencies, give some largish range from say 1 to 10 gigahertz. You don't need a big step size here, so maybe 0.1 is more than enough. Make a new graph. Add a measurement. Go to linear. Port parameters, you want S11, right? That's the reflection coefficient. And I can look at the magnitude in dB, maybe. Actually, let's just look at the magnitude. Right. Okay, so it's showing a reflection coefficient of something which is fairly small. See, this is, look at the axis, it's 0.02 and 0.06. And it's changing as a function of frequency. And it's actually reaching 0 at this particular point. So does this mean that the transmission line is 50 ohms? Huh?
This is the frequency they're sending.
Well, they are sending all these frequencies. So the response corresponds to the frequency shown on the x-axis. So why is the reflection coefficient non-zero here, but 0 here and again non-zero here? Does it mean that the transmission line has different impedances, characteristic impedances at different frequencies? What's going on here?
Different frequencies could have different phase velocity.
Well, this is supposed to be a simple, okay, it's microstrip, it's not perfect, but it's not supposed to have frequency dispersion. Let me do something which should give you a hint. Okay, I'm going to freeze this. I'm going to change the length of the transmission line. I'm doubling it. Remember that the length of the transmission line has no effect on the characteristic impedance of the transmission line, right? Ishita, now can you tell me what is it I'm looking at right now? Why is it like this? I've plotted the magnitude of the reflection coefficient as a function of frequency. The circuit is a transmission line we are trying to design. So it has some characteristic impedance. So let me at least clarify that part. It's not that the characteristic impedance is changing with frequency. It has some characteristic impedance. We don't know what it is. It's something we want to make that 50 ohms because we don't know the exact dimensions to choose for that right now. It has some length. There is 50 ohm on one end connected, and I'm looking at using a port. I'm looking at the reflection coefficient at this point. So I'm looking at the gamma here. Does this look familiar?
Yes, standing is at those frequencies. You don't get any.
And that happens when?
When wavelength matches with the lambda by 2.
Is it lambda by 2?
Lambda by 4, 3 lambda by 4, 5 lambda. Lambda by 4, 3 lambda by 4, 5 lambda by 4.
Well, I mean, I could be confusing you. Is it lambda by 4 or lambda by 2? You can sort of see from here, this frequency and these frequencies are related by a factor of 2, right? So, okay, what does this mean? That at these frequencies, there is zero reflection at this point, right? Which means that this whole thing looks like 50 ohms. Now we know that this is 50 ohms on this side. So this we know is 50 ohms. Huh? Okay, I think I accidentally touched something. So there are a few possibilities, right, which we have learned. Now, maybe this is behaving like an impedance transformer at those frequencies and transforming. But the thing is, this is already 50 ohms. So it cannot be a lambda by 4 transformer. It cannot transform 50 into 50. So which was that other length we had checked, which actually doesn't do anything. That's lambda by 2, right? But lambda by 2, you are getting that this basically doesn't do anything, right? This part doesn't do anything. So this must be like lambda by 2, this is lambda, and so on and so forth. We can check something where if I make this 40 ohms, then I could definitely have a impedance transformer kind of behavior, right? So I've made the load 40 ohms. Then the only way I can get zero reflection at this point is if this gives me a lambda by 4 type of transformer. Okay. But we know that in order for that to happen, the characteristic impedance of the transmission line, so let's call that Z0. At lambda by 4, what is the input impedance here? Z in is Z0 square by 40. Is that right? Am I remembering it correctly? It's the characteristic impedance of the transmission line, right? Squared divided by 40. And this we want to be equal to 50 ohms in order for the zero to happen. What we are seeing now is that the reflection is always non-zero. So from this behavior, can you guess something about Z naught of the transmission line we have made? Because we don't know what the characteristic impedance is, right? Huh? No, that we have already established that it cannot, right?
Like, so if we calculate Z naught over 0, right, we get 30. So it's definitely.
Sorry, Z naught for what?
If we calculate Z naught for this, it's where we get the match.
Oh, you mean if you calculate this, if you calculate what Z naught should be in order to get a match, you have, what is this? So 20, it's like 2000, square root of 2000, right? So is what?
I'm just saying that this is for
So it's not matching. What does that mean? Let me freeze this. I have to warn you that I'm not sure what's happening. I think I know what's happening, but I'm not sure. I now made this 60 ohms. And it's behaving like this. I still don't get.
The impedance is not matched. The deflection coefficient is just greater than than not so
No, that's right.
why we are
No,
getting
no,
more
no, no,
data
no.
in this case.
No, no, that's right. See, the point I'm trying to make is that there is no frequency. By looking at this curve, what is this? Is plotting the reflection coefficient at this point, the magnitude of that. What I'm saying is that at no frequency, it's zero. Which actually is, for an impedance transformer, it's not surprising, right? Because there is one frequency where the matching will happen, but the matching will happen only if the magnitude of the impedance is, the transmission line is correct. Okay. Now, if I tune this, let's put this on a tuner, and what's the, I'm matching to 60 ohms now, right? Now, so right there, I get, so this is 930 is the width. And now at this point, it matches, which is, what is the frequency? 1.8 gigahertz. This is 5.4 gigahertz. So this is now going 3 times, right? So this is like lambda by 4, 3 lambda by 4. So if this is now matching and this is the quarter wavelength, that means Z naught here is 60 into 40. Square root of that. It's about 48.9 ohms. I can't hear you, Panya.
So we wanted to match the 50 and low risk.
Yep. So,
Should be 50.
Hmm?
It should be 50 to 60 there.
no, so Z in is, we are not matching 60 to 15. Okay, yeah, I mean, it's basically Z naught square over ZL, right? And we want this to be 50. So that means Z naught square. So this is equal to 50. Yeah, so then that means Z naught is 50 into 60. Isn't that what I did? No? Oh, I did 40 into 60. Sorry. 60. 54 ohms. So it's now saying that the transmission line we have made has 54 ohms close to it. It's not, it won't be exactly accurate, but we can now check this by making this 54 ohms and making this also 54 ohms. And then we look at the response and see what we get. Close enough. Right? So we are somewhere close to that value. But what we really want 50, so we can look at this and open the slider. So 54 means we have to come lower, which means we have to increase the width, which is what now I'm doing. So now you can see that it always remains a lambda by 4 transformer at those exact frequencies, right? All that is changing is how much it's deviating from there. So the closer you are to 50 ohms, it's going to remain closer and closer. Now gone too far. Somewhere around there. Okay, if TX line was working, we could check that something close to 1.1 millimeter is what would give you. But based on playing around with this this dielectric board, I know that this is close to being correct. Maybe let's try once more if this works. It's fine. It's very bizarre. How can it? So let's take 6, height 762. Width is 1110. Conductivity, let's make it some very large number. 50.4 ohms. So this verifies what's going on. So the reason I actually spend a little bit of time on this is that this is one way you can, by understanding how the reflection coefficient would change, if you're dealing with an unknown transmission line which you have designed, you can actually guess, are you above or below 50 ohms, and sort of know what to do to get to the right. Because here, of course, I could just change the numbers continuously till it matched. In a real thing, you cannot make infinite number of transmission lines with varying width to get it correctly. Okay. So yeah, and another point is that when you're doing, if you're trying to use these kind of techniques to figure out, it's important that you keep the length at least several wavelengths over the range of frequency you're interested in, because otherwise you can actually be fooled if you look at a very narrow range of frequencies, because you will not know whether you are mismatched, especially if you use very low frequency numbers, because at very low frequencies, the transmission line is essentially non-existent. It's in terms of the number of wavelengths, it's very small. So you will actually always get matching. If you, even if so if this was 50 ohms and that was 50 ohms and this was anything, but you go to 0 frequency or very to kilohertz frequency, then it's just like a piece of wire. It doesn't have any role to play. So it's important to keep it long enough that there are several wavelengths so that you can see this kind of a periodic behavior, and that will then tell you what's going on with the transmission line. So similarly, you can do the same thing for coplanar. So here again, you go to lines, and then you can use this CPW line here, this one. Okay, so now it gives you 3 dimensions: the length, the width, and the gap. This also has its substrate definition. Let's see if the same substrate definition works or it has a different one. This one has its own one called CPW sub. So that you have to find from it's not responsive now. So you go to substrates, and then you find the CPW sub here. It's right here, the top one. Okay. So since these are 2 different transmission lines, you can have them probably on the same structure. It doesn't matter. It has some huge number of different things, which you can check in the help file and see. Essentially, it should have the same dielectric constants, but there are probably some additional. Yeah, see, it even gives the option of having, if you have a metallic cover which is very close, right? So if you go to your, so I had mentioned this for the ground plane for the CPW underneath, but the same argument applies if it is on top as well. If you have a ground plane which is very close, then it starts to look like a strip line version of the CPW, but with air on the top side. So a ground plane very close on the top also can have an impact, and this model actually allows you to take that into account. But as long as it's far away, it would actually not matter. Okay, so then same for strip line. So I would suggest that you try playing with these things to get familiar with these different objects. And this again are pre-solved models. So rather than a simple electrical model, this actually takes into account these dimensions and comes up with some effective formulas and then uses that to do the computation. So if you're trying to design something, using this will give you closer to the results you have in your actual setup. But if you really want to exactly, or again, not exact, but as close as possible to your real setup, you need a full finite element simulation, which means you define the full structure. You're actually going to define. I'm going to just very quickly introduce you to that thing that's under this thing called EM structure. Say new EM structure. And it has several options for solving it. Not all of them are available with the software, but the one we use is the first one called Axiom. So when you create that, you get again a window like this, but now here you don't drag and drop components. Instead, you draw some stuff like this. Okay. So you can, so see when I'm drawing, I get dimensions here. So it's showing dx, dy. So this is now the dimension of the metallic plane you're drawing. So if this was a microstrip transmission line, this would be the x-axis would be length and the y-axis would be the width of the transmission line. For this, you have to specify something called an enclosure. This basically takes care of the vertical part of the thing because it's effectively a 2D solver with some way it takes into account the third dimensions. But I'll go through this in more detail in the next lecture because this requires some. So basically, you have to specify the different dielectric layers you have. You specify what is at the bottom, you specify what is at the top. You can have multiple dielectric layers, and then you specify where this metal is going to be. Where, because in a microstrip, it's on top of the dielectric. In strip line, it's in between 2 dielectrics, even though they are the same. So those kind of things you can specify here. And then once you have the structure, I mean, this is basically just a microstrip, right? This microstrip won't be anything more complicated than this. So then you have to put ports, and this has a special type of port which you can go from here, draw, add edge port. Similarly, you do one on this side. And then you set up the frequencies and then it will solve. As I mentioned, the finite element solver is much slower because it's actually solving Maxwell's equations by breaking this up into different things. So there is a concept of called meshing. So if I go to this right click and say mesh. It has probably thrown some error. Let me see. Yeah. Okay, I'll show you this next time. I think there is some license feature. That's strange. But essentially what it would have shown here is how it has broken up this rectangle into small polygons, and that's how it solves it. I mean, that is, you don't have to check anything there, but sometimes if you have structures which have large features and small features, you might want to control the meshing so that you ensure that the small features have final meshing, otherwise you'll get inaccurate results. So this allows you to actually set up transmission lines quite conveniently, and you can simulate it to see what you would get. So in the next lecture, we will look at this in detail and then do a comparison from the simplest model, which is the electrical model, to the physical model, and then to the EM structure. Okay. So it's 4 o'clock. Let's stop there today. Any quick questions?